gravitational fields. Oh, yeah. Now, is this going to change the background color, or is it just going to write nice? Okay, good. Gravitational fields. Now, in physics, fields can cause some consternation, okay? So what do I mean by consternation? I mean, like, if you ask me what is a field, I might give you an answer that you don't necessarily like. So what's a field? Well, I'm going to give it to you like this. A field is an area. Yeah, that's right. In space where a force of a particular type acts. Okay? Yeah, that's right. Deal with it. So what is it? Is it a thing or is it not a thing? Well, I don't know. It's an area. Okay? Let's do an example that will maybe help make sense of this. So this is meant to be 3D, but let's draw a mass. Okay? So we've got some mass here. Now, if we take another mass, this is going to look familiar here. Let's make it this color. And I put it over here. Okay, this is another mass. We might recognize that this is kind of like, and we say maybe this is going around in a circle. We might say that this is a planet and a moon, or like a sun and a planet, or whatever, or like the center of a galaxy and a star, some orbital system. Okay, and then we think about Newton's law of universal gravitation. That just looks like this. If this is r squared, okay, well, we know some things, right? We know that if we move this out farther, that the gravitational attraction between these two objects will decrease. It will decrease at a squared distance. Or if we move it closer, okay, it will increase at a squared distance. If we have the distance, we get 4 times the force of gravity, and so on, right? So where does field come into this? Well, we say that the area in which these feel a gravitational force to each other is the gravitational field, okay? And we draw fields with arrows. So with a gravitational field, we know that it's always an attractive field, and therefore the field will always have force vectors pointing in towards the center of the major mass, or the smaller mass for that matter, okay? So now you might say to yourself, well, this is a mass too. Does it have a field? We could say, yeah, sure it does. And then you could ask yourself, does this have a gravitational field when there is no other mass nearby? And then I would say to you, if a tree falls in a forest and there's no one there to hear it, does it make a sound? If there's no other mass, is there still a gravitational field? I'm going to just draw this guy, I don't know. Maybe. Okay. But really, whether that field is actually there or not, if there's no other mass, is sort of irrelevant. It doesn't really matter. Okay, we can work with this as it is. So this is kind of a function, right? We call this a function, right? And this function is true in gravitational fields. So some people say that a field is like a function that tells you, if you put in the right numbers, what, in this case, what force you're going to have depending where you put an object in that field. I don't know if I like that explanation, but I mean, it kind of makes sense, I guess. Okay. So a field is like an area around a mass, as long as there's another mass there to detect that force, okay, in which gravitational, in this case, attraction acts. Now, there are other kinds of fields. There's magnetic fields, there's electric fields. You could almost even say there are things like light fields, maybe not, like areas where other things would be illuminated by a light source. You might say that's a light field. Although I might get slapped for saying that by other physicists, that's something that kind of helps me think about it. Okay, and so hopefully that helps you understand what a gravitational field is all about. So if you look here, we can look at the density, if you want, of these arrows as sort of a visual way of looking at how that field would taper off as we move away. Okay, so now we see that this is one of those famous in physics inverse square laws. So we know this about gravity, right? That it is proportional to 1 over the radius squared, or the inverse of the square of radius, or an inverse square. But it is also proportional to your m's, the masses that you're dealing with. Okay? So why should this be so? Well, there's something about mass, right? There's something about mass that creates a gravitational field. Later on, you can get really technical about it, and you can talk about it in terms of like the bending of space and so on. We're not going to go there. We're just going to look at this in a Newtonian way, like Newton did, where you have sort of static space and it's empty, and fields act on other objects and cause forces to exist, right? So that being said, let's just reiterate why we have an inverse square situation going on here. So let's say we have this. Okay, now we're gonna have to imagine this is in 3 dimensions, right? So I'm gonna draw the like little 3-dimension symbol on here, the warped window, you know what I'm talking about? And then let's imagine that we have some arrows pointing out to the center. Okay, see if we can, so you can work with me here and understand what I'm trying to draw. So what I want to draw here is like a surface. Okay, so I got a surface, and it's going to be like curved like that, like that. Okay, and I'm going to draw it back over here. Okay, now imagine that our field, right? Our field lines are, oops, I want to draw arrows. Let's imagine that our field lines are like pushing out from the center, right, through here. And we want to know like the density of the field through each of these surfaces, right? So how do I find the area of one of these surfaces? So I got to start first with the area of a sphere, don't I? How do I find the area of the surface of a sphere? Surface area of a sphere. How do I do that? So it's 4 pi r squared. Okay, 4 pi r squared. So then we're talking about area here. Now let's say that this is r, all right? So right here is the surface of the sphere, this area, and we're just talking about like a section of the sphere, but you could be talking about the whole sphere, okay? This is 2r, and this is 3r. So what does that tell you about these sections? Well, at r, right, the area, let's say is 1. Okay, let's say the area is 1. Does that make sense? Well, what's the area going to be when we have 2r? Let's put a 2 in there. It's going to be 4 times larger than this, is it not? Right? It's going to be 4. And then when we're at 3, it's going to be 9. Okay, so the area is going to be 9. So then if we talk about the density of the field lines, the density of the field lines passing through the surface, if the area is going up this way, what's happening to the density? It is doing the what? The inverse of that, is it not? We've got 4 times more area, but the same amount of field line density, then we should have 1/4 of the overall density of field lines. And then we should have 1/9 of the density here. So because of that, we could say that the force, right, if we say correlate force to the field line density, so this is just a geometric argument, the force should then be proportional to 1 over just the square of the radius. Okay, so this is kind of an explanation for inverse squared relationships, I guess, in terms of why it's true with fields. Okay, so then what I could imagine, okay, is if I were to place an object of set mass here versus here versus here at, you know, r, 2r, and 3r, the amount of force should be, right, 1/4 and then 1/9 And then if I double it again, a 16th, and so on. Okay? So the force drops off at a squared distance. Is that a good explanation? Does that make sense? Now you see inverse squared relationships in a lot of places in physics. All right? The way that sound power drops off as you move away from the source. The dimming of light as you move away from a source. Electric field drop off. Magnetic field drop off, and of course gravity drop off. Okay, all of these behave inverse squarely, and that's got to do with the way that, I guess force permeates 3D space. Not force, but fields permeate 3D space. Okay, so now let's talk about the strength of a field. Field strength. How do you think we measure the strength of a field? How would we do that? What units do you feel like field strength would be measured in? Okay, newtons. Field strength is in newtons, but it's got to be related to this, right? So gravitational fields work on masses. So really, it's got to be newtons per kilogram. Or if you want, force per mass. Force per amount of mass. So what we're saying here is, okay, this is like a general idea, but at this point, how much force do we get for a given mass, right? Here, how much force do we get for a given mass? It'll be less, right? How much force do we get for a given mass here, 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 and here, right? So now we're developing another function to describe something about this field. If we put x mass here, how much force will it get? If we put x mass here, how much force will we get? So how do we do that? Well, we just say then that field strength, G, should be equal to the amount of force we get per unit of mass. At the surface of Earth, what is the gravitational field strength? How much force do we get for a given amount of mass? Well, we should get 9.8 newtons for every kilogram of mass. Should we not? Is that not what we get? Do we not get 9.8 newtons of pull for every kilogram? So what does that number look like to you? Doesn't that look like the acceleration due to gravity? Well, watch this. What's inside a newton? It is the same unit. So what we're talking about here is an acceleration. We call field strength acceleration generally, but it has the same units as thinking about it in terms of how much pull you get for each unit of mass in that field. Okay. Now I wonder if we can pull this number out of Newton's gravitational field law. I bet we can. Let's try it. So here we are, right? If we know some stuff about the Earth, we should be able to get this value out of nature. Okay, so let's say we've got a radius right here, okay, and we've got a mass sitting at the surface of the Earth, okay. Well, we would say then that Fg should be equal to big G mm all over r squared, okay. And we would also say, by definition, that F equals ma, except we're talking about a special a here, aren't we? We're talking about the acceleration due to gravity at the surface of the Earth, which is also the way that we describe the field strength at that point. So G. We did basically touch on this last time, but then we can make these two things equal, right? Like Fg equals mg, and Fg should also be found by this, equals big G, universal gravitational constant, times both masses divided by r squared. So here's that mass we're talking about, and it appears in both places. So we can just cancel it off. And we have a way now of figuring out G, not just at the surface of Earth really, but anywhere around the planet that you want to go out in space and so on. So let's see if we get the number that we expect. What value do we have for universal gravitational constant? What is it? What units does it have to be in? Times what squared? Good. Okay. Times the mass of the Earth. I think it's 5.24. 5 times 10 to the 24. Yeah, that was close. Close-ish. 5.97 times 10 to the 24 kilograms for the mass of Earth. And then the radius squared. What is the radius of our planet? Is it not 6.3 times 10 to the 6 or 6.3 million meters? I believe that's right, because I think it's 6,300 kilometers, right? And then that's got to be squared. Now this should give us roughly 9.8. Hope it does. So we use some like imprecise numbers, but you get roughly exactly what you'd expect, somewhere around 10 meters per second squared, which is, you know, with the amount of rounding that I did here, roughly equivalent to what we would expect at 9.8 meters per second squared. And if we just go through and we do our canceling off, you're actually going to end up in terms of newtons per kilogram. Okay, so meters squared cancels off. One of these cancels off, and there you go, newtons per 1 kilogram. Okay, so newtons per 1 kilogram, just as we would expect, newtons per kilogram. All right. What else do I need to tell you about? Okay, so last time we also talked a little bit about Cavendish, and that his original goal was to find the mass of Earth. Mass of Earth. How do you go about doing that? If you have G, you can. Okay? Right. Absolutely. So, you know, once Cavendish had figured out G, you can find out any number of things, right? You can measure G with a stopwatch and dropping some objects. You can actually find out what it is. This is the mass of the Earth, right here. So you can just rearrange this formula to solve for the mass of the Earth. So here's what we're saying. Here's the mass of Earth. It's got a radius, okay? We've figured out G by experiment at the surface, okay? So all we got to do is isolate that. So the mass of the Earth should be found based on this as G times the radius of the planet squared divided by big G, okay? So we give that a try. So 9.81 meters per second squared divided by 6.3 times 10 to the 6 meters, and square that whole thing and divide by G. Okay, and we should end up with an answer in terms of kilograms at the end of all of that. And what do we get? And if you think about this as newtons per kilogram, it makes more sense as to how you end up with kilograms at the end. So 5.8 times 10 to the 24 is what I get. Okay, let's try one more thing. Okay, let's try this. Let's see if you guys can find the mass of Jupiter, given some input information. Okay, you know that one moon of Jupiter, Ganymede, has a period equal to, was it 178 hours? Shoot, I forgot. Sorry, 172 hours. Okay, and we're also going to find out that the orbital radius is, okay, and it orbits roughly at a mean distance of 1.1 times 10 to the 6 kilometers. So let's just draw a little picture of this. So here's Jupiter. I'll draw it if I can. What color is Jupiter? It's like red, isn't it? Light red, orangey, kind of orangey. It's got the big spot on it. Okay. And then we're saying we got a planet here, or a planet. We've got a moon. It's a big moon. It's a fairly large moon. We got a moon here. And that moon is zipping around, okay, at a radius of 1.1 times 10 to the 6 million kilometers. So from this info, okay, find the mass of Jupiter. So this is going to take into account a couple of things. One, the centripetal force here is provided by the gravity between these two objects. Okay, so that's important. You need to think about centripetal force. You also know that you have different ways of solving for FC. So the one you're going to want here is 4 pi squared r all over t squared. And you're going to want to make that equal to, and sorry, there's an m on there, my bad, m 4 pi squared. And you're going to want to make that equal to gravity. And you know from Newton's law, g m all over r squared. So with this information, find me the mass of Jupiter. All right, so we have to do a couple conversions here first. We can't deal directly in hours because that's not the units that we work in, right? We have to be in m, k, and s. That's the units that newtons are measured in, and so on. So we have to be in seconds and meters. And we have to say the centripetal force is provided by gravity. So Fc equals Fg. So then we can say m, mass of Ganymede, 4 pi squared r, derived that before, all over t squared, has to be equal to big G, mass of the planet Jupiter, mass of Ganymede, right? So that's mass of Ganymede, divided by the mean orbital radius squared. So we come here and we realize that the mass of the moon gets deleted off both sides, and we are after this, figuring out the mass of the planet. To do some algebra here, that the mass of the planet should be equal to, well, bring r up over here, 4 pi squared r cubed all over t squared. And then you put in your numbers. All right, sorry. Don't forget your g. My bad. G's got to come down here. Thank you. All right. I was like looking at that. I was like, something isn't quite right. Okay. I'm going to be lazy and leave off my units. So this should give us the mass of the planet if we can plug it in right. So this math here, if you do it correctly and you give it a try on your own, gives you about 2 times 10 to the 27 kilograms. And if you look up this value, you get 1.8 times 10 to the 27. So sig fig wise, I would say these are equivalent values. And you can't actually go and measure a planet, but you can estimate, like measure its weight. There's no way to directly measure it, but Newton's law is good enough to give us a fairly accurate estimation of the mass of these objects, just simply taking in stuff that you could observe. You could observe the period of Ganymede, and I don't know exactly how it's done, probably like with like arc length and so on, figure out the distance away that the moon is from the planet with the telescope. Okay, and you could do that for all the planets. You can figure out their masses. You could also, of course, if you know some other things, use its relationship to the sun. That'd be another way to sort of figure that out, right? If you know Jupiter's distance away from the sun, okay, there's a way to do it with that. Again, Fc is equal to GMM, and figure out the m of the planet if you know the mass of the sun. I would say this is probably the most straightforward way, because all you need is its period and its distance away from the planet. Okay, but it also brings up some interesting questions. What if you change the mass of a planet? What happens to it in terms of its relationship to the sun and its orbital radius? Would it change? And what's important there? If you want to know the distance away from the central mass, what sorts of input values are important in figuring out where something is going to sit in its orbit? Is mass important? Or is distance away important? Or is velocity around important? Or is period important? And what you'll find out is the distance away dictates the period of the orbital object. So here's your homework. Find the orbital radius of a geosynchronous satellite? Because there's only one place that you could ever have a geosynchronous satellite. It doesn't matter about its weight, it matters about its period. If you don't know what geosynchronous is, it's the kind of satellite that your satellite TV comes in on, where the satellite stays in the exact same position above the Earth as the Earth turns. Sorry, I drew that wrong. Okay, if this is the equator, then we're kind of going around like this at the exact same rate that the Earth spins. So what would the period of a geosynchronous satellite have to be then? How long does it take? Yeah, it's got to be 24 hours, right? It takes the Earth exactly 24 hours to spin once. So the satellite, geosynchronous, means it stays above the same spot on the Earth the whole time. This is important, right? Because you put a satellite dish on your house and you point it one time. It's got to always line up with the satellite. Otherwise, your satellite dish would be like zipping around trying to follow the satellite, right? So what is that orbit and how do we find it? What is that orbital radius and how do we find it? All right, so you're going to use the same mentality you used here. Here's the mass of your satellite. It's gone. So you need G, you need the mass of the Earth, which we found out another way, and you want to solve for this. All right, so let's just finish this up. Solving for R. So we'll cross multiply first here. And we'll solve for R. And we want the cube root of that. So the number's in. Mass of the Earth. We just calculated it. What was it? 5.8 times 10 to the 24. There it is. These numbers are hard to remember. kgs. We got 24 hours times 3,600 seconds per hour. Just square that. All over 4 pi squared. All right, if you've done your math right, to get to cube root it, you should get something like 4.2 times 10 to the 7 meters. Okay, now that's as measured from the center of the Earth to the satellite. You want to know the distance above Earth? Well, you just simply subtract the radius of Earth, and that will give the altitude. There you go, geosynchronous satellites.